laws, force stuff. So I got a question for you. When you step on a scale, what are you measuring?
Weight.
Are you measuring weight or mass?
When you say scale, gravitational
scale are
force
you
on
talking
your mass?
about?
Like you mean a bathroom scale, or is it like an actual?
Scale.
Okay, so I'm talking about a scale, which is different than a balance. I'm talking about it, like, just say for example, a bathroom scale. What do you measure?
Weight.
Measuring weight. Okay, you might, now, are you measuring both or just weight? Both, when I say both, I mean probably weight versus
You're
what?
measuring mass on Earth.
Okay, so you're measuring, okay, so if you want to find your weight or your mass, if you're careful, you could use a bathroom scale to do both, right?
Yeah.
Okay, but it's directly measuring weight. Okay, how come? Because what is a bathroom scale? Bathroom scale, if you step on it, all it is, it's got a spring, and as you displace the spring, it's calibrated so the distance that you displace the spring corresponds to a weight. So it's calibrated so amount of displacement is correlated to the force that's displacing the spring. If you're just standing there at rest, well, what's the only force acting on the scale? Yeah, your weight, right? But what it's really measuring that indirectly, because actually what it's measuring is what we call normal force. It's really not measuring your weight, it's measuring the amount of force that the spring is having to apply against you to keep you from falling through the floor, right? Does that make sense? So if you look at it from the perspective of the scale, this is what's going on, right? Here's the ground, there's the scale, and if you're standing on the scale, right, then what it's really doing is it's pushing up on you, right? If you think about the forces acting on you as a free body diagram, you've got your weight pushing down, right? And what's pushing up? Well, the normal force. Normally it's the ground, but if you're standing on the scale, it's actually the scale that's taking the place of the ground and is pushing up on you, right? What do you think is going to happen if, let's just say you step into an elevator and there's a scale, there's, oh, well, let's check my weight. You step on there and it's fine, it looks about right. But what happens if the elevator starts to accelerate upward? Okay, your weight, does your weight actually increase?
No.
No, you didn't.
Force.
Okay.
Going down.
The normal force applied by the scale is increasing, isn't it? Right? Now you can probably kind of just conceptually say, yeah, that makes sense, right? That the scale's having to push harder. You'd feel more force under your feet, wouldn't you? You actually feel something. If you're in an elevator that's accelerating upward, you feel a little bit heavier, don't you?
Yeah.
Right? And why do you feel heavier? There's a lot going on here, but this is kind of interesting way to think about it. What you really associate with weight is not any kind of intrinsic feeling of gravity acting on you. Not at all. You can't feel gravity acting on you. You couldn't tell the difference if you were in, well, you tell me, could you feel the difference if you were in free fall versus if you were floating in outer space?
No.
You couldn't.
Actually, so
Taking out the wind, ignoring, so say we evacuate the place where there's no air.
ignoring air resistance.
Ignoring air resistance, you couldn't tell any difference, right?
Isn't there like something in your ear that tells you?
There's, well, okay, so your inner ear, you're gonna notice acceleration, sure, right?
But if you're at the constant speed.
But you're not gonna feel
Yeah.
anything intrinsically on your body, because like what you associate with weight is actually the pressure on your feet.
Yeah,
Right.
If you're at a constant speed, then fluid in your ear would be moving at the same speed. So.
Well, right, but if you're accelerating, it would be,
Yeah.
then you actually would be feeling, you would feel the acceleration, but you're not gonna feel anything in terms of exterior forces acting on you. What you associate with your weight is just the force, right? And so you feel like when the elevator starts to accelerate upward and accelerates you upward with it, then you're gonna feel some extra pressure on the bottom of your feet, and you're gonna associate that with being heavier. And so you would probably describe it as I feel heavier, right? That wouldn't be abnormal, and you'd be right. That's how you sense the weight is that pressure. Let's look at that in terms of a free body diagram. So if you're at rest in the elevator, what's the net force? Zero. Okay, if the net force is zero, what's our relationship between net force and acceleration? Do the second law. How does that go?
Force is acceleration.
Yeah, net force equals
Acceleration
times what?
times.
Mass, right.
And
MA, right? Okay, so mass is what, that's inertia, right? That's the quantitative version of inertia. So the amount of mass you have determines how much acceleration you're buying for a certain amount of force. Agreed? Okay? So if we're at rest, then the net force is zero and there's no acceleration, right? But if we're accelerating upward, right, then that means if there is a positive acceleration, what does that tell you? If there's a positive acceleration, there also has to be a positive net force, right? So the sum of the two forces cannot add to zero because these two things always go together, right? Net force and acceleration always have to go together. You can't have one without the other. So now we've got a positive net force, and so let's just make this our net force vector. So if our net force vector is pointing up, what does that mean? What had to happen to our free body diagram?
Gravity's going bigger.
Gravity's, but mg, your mass is a proper, g is a pseudo constant. G just stands for the acceleration of gravity at the Earth's surface. It's not actually a constant. If you can, scientists, like geologists, geophysicists actually, they'll map the kind of the composition of the interior of the Earth by using real sensitive gravitometers. Like you can measure local differences in gravity, and you can turn that into, like for example, we would have sort of higher gravity in Eastern Oregon than we would on the coast because we've got basalt under us, and basalt is a dense rock. On the coast, they've got lots of sandstone, and that's not as dense, and so you'd weigh slightly more in Pendleton than you would if you went to Cannon Beach or something, right? And so by just measuring those slight variations, you can actually kind of map out the types of materials that are under your feet if you were to go burrow down into the earth. Yes?
so how slight is the variation?
Oh, extremely slight. I mean, wouldn't even be measurable. Like on your bathroom scale, it would be just a fraction of a fraction of a fraction of the thickness of just that little needle that tells where the scale is pointing. You would never be able to tell. But if you have really sensitive equipment, like geophysicists do, then yeah, you can do that. So anyway, I digress. So G is essentially a constant, right? For the purpose of this problem, it is, right? Because you're just riding in an elevator, right? You're not moving huge hundreds of miles in one direction or the other. And M is absolutely a constant, right? Your mass is just, that's an artifact of all the stuff that makes you up, and that's not changing during the course of the problem, right? So this can't change. Your actual weight, meaning the force of gravity acting on you, is not going to change. So what is changing?
Your acceleration.
Well, yeah, you're accelerating, so which one of those forces has to be the one that's changing to cause this? Understand that the red vector is the sum of those vectors, right? Net force is not an additional, it's not something you would add up tip to tail with things like weight or normal force, right? It's the result of adding up all the actual forces, right?
Normal force, that'd be a normal
Yeah, the normal force must be increasing, right? If we're accelerating upward, that means that the normal force has to be that much longer than the other force, right? And so I'd have to go up here and extend this vector a little further up, right? What does that translate into? Well, the normal force is the pushing force of the scale, and so if you look down and read the scale, when you're accelerating upward, what are you going to notice?
It's gonna get heavier.
Yeah, it's reading a larger force. So we call that apparent weight. It's not actually your weight, but it's what we associate with weight as the normal force, right? So your apparent weight is increasing, right? Okay. What about at the top of so the elevator accelerates up to speed, and now it's just going to move up at constant speed again. If it's moving up at constant speed, what's the net force? How come? You're right. How come?
Because it's not accelerating.
Yeah, it's not acceleration, because by definition, constant speed means that, or velocity, because we're going in the same direction, means that the change in velocity, the rate of change of velocity is zero if it's constant. And that's what acceleration is, right? Change in velocity over change in time. Well, the velocity's not changing. And so if we're moving up at constant speed, then all of a sudden the net force is going to, it's going to shrink back down to zero. And the length of this vector goes back down to where it was, so that these offset each other, right? But now you get to the top of the right, and you're having to slow down to get to the top, right? Well, when you're slowing down in the positive direction, what is that? So your velocity is changing in which direction?
You're accelerating in the negative direction.
Ah, okay, yeah, that's negative acceleration, right? Remember the invisible hand thing we did up here?
Yeah.
Right, if this is the positive direction, and I'm moving in the positive direction but slowing down, the invisible hand is actually pushing me in the negative direction, right? Now the invisible hand has a little more meaning though, doesn't it? Because the invisible hand represents the hypothetical force that's causing the acceleration, right? See that correlation? Okay. So this guy's gonna get smaller, and what does that feel like?
Feels you're getting to the top.
Yeah, you'd say I feel lighter, don't you? Right.
He's going faster than the.
Well, but to you, you're gonna feel less pressure, and you're gonna feel like your weight is reduced, right? And then the ultimate would be if the elevator cable broke and the thing went into free fall, then what would the force acting on your feet be? Well, what would it be?
Zero.
It'd be zero, right? It'd be zero. And so the only force acting on you would be weight pushing you down, but you wouldn't feel any pressure, and you'd say, I feel weightless. Well, are you weightless? No, your weight hasn't changed, but once again, the way we interpret weight is through normal force, and you're apparently weightless. So you could do tricks like this, not just in an elevator. You could do this, for example, this would go back to the space station, right? We could easily fake gravity on a space station by just spinning the space station. And we'll talk more about that when we get to rotational physics, but everybody agree that if we did that, so let's say there's the outside edge of the space station, and then you're walking around on the surface of that, and it's spinning like so. The rate at which you spin that is going to determine how much force is required to push you towards the center, and we'll get to that later. But if you were standing on a scale, the faster this thing spins, the greater the reading would be on the scale. So it'll make more sense, like I say, in the near future, right? But that's apparent weight also, isn't it? Because once again, you're feeling that pressure that the scale is measuring, and so it acts just like normal weight. And it actually does the job it needs to do. It prevents your body from atrophying and your bones from decaying and being absorbed, all the calcium being reabsorbed into your body, and you can stay healthy as long as you have a big space station that you can spin. Okay, so that's good to know about. Let's talk friction. Let's talk friction for a second here. So another force that I want you to become familiar with is, or you have to become familiar with, a really important one is friction. So what is friction? Tell me some things about friction.
Resistance.
What is it? Okay, it's resistance. Now that's an important word. It's resistance in the sense that if I'm moving in this direction, in what direction is friction necessarily acting? Opposite direction, right? The friction that's acting on me is acting in the opposite direction of the direction that I'm going, right?
Does there have to be movement of friction?
No, there doesn't have to be movement. There doesn't, and we'll get to that. You're right. So friction is going to resist motion, right? If an object is moving and I push it and I let it go, ooh, that's kind of bad. Yeah. How about this instead? So if I push something and let it go, the friction is going to stop it, right? The friction is pushing against it and it brings it to rest. What causes friction? Now let's talk sliding friction. And there's different kinds of friction we can talk about here. So what do you suppose causes sliding friction?
Weight, slide, gravity.
Well, okay, I mean, indirectly, maybe weight does, I guess, indirectly, but what's mass indirectly? What's causing it directly? What do you think is causing the friction?
Surface tension or
Surface area.
It's, you're kind of flirting with the right answer. It has to do with surfaces, and it just has to do with the interaction of the surfaces. That's all it is. The smoother the surfaces are, the less friction there's gonna be, right? So if we push this object in this direction, then if that's the direction of motion, then the friction is going to resist us in that direction. Right? That's our frictional force. Why are some, in some cases we get stronger friction than in other cases. There's two things that affect it. One of them is the composition of the two surfaces. So if you look at a microscopic level, surfaces are not smooth. Even if you take something like polished metal, which is about the smoothest surface you can get, at the microscopic level, what's it look like? Instead of being like this, they're going to be, it's broken up into discrete atoms, and so the surface is going to be kind of bumpy at some level. At some level, those bumps aren't even real bumps anymore. They're just, you have relatively strong and weak electric fields there, right? And that's really what's causing nothing. Let's get this out there too. There's no such thing as stuff. It's solid stuff. This seems pretty solid when I knock on it, but in actuality, well over 99.999% of that is just empty space, right? There's really nothing solid there. When you touch something, it feels really solid, but what you're actually feeling is the repulsive electromagnetic force between your hand, atoms of your hand, and the atoms of the table, right? So it's a pretty good model for us to think about things as being solid on our scale in the everyday world, but in reality, they're really not, right? So if you get two objects that are, if the bumps are big, relatively big bumps, it's not highly polished, then as the surfaces move past each other, these bumps weld together. When they get too close together, they're welded together, and then you got to break them free by moving them forward. And they'll kind of, they kind of do like this, right? They'll stick together, and then they'll flex, and they break free. All these bumps in the objects on the surface. And the more strongly those bumps weld together, and the more bumps that you have, the stronger the frictional force. Okay? So that's really all a frictional force is. The other thing, though, that seems like it ought to have some impact on how strong the frictional force is then is not just how many bumps there are, but how strongly you're pressing the forces together. Would everybody agree that if you press down on something really hard, it's harder to move it across the surface than if you don't? Right? Because you're pushing the bumps together harder. Yes?
But wouldn't that correlate to how much weight something has?
Well, okay, it might be weight, but it might also be the direction in which the force that's moving it is being applied, right? If you're pushing, like we know that if I want to slide something across the surface, do I want to push from that angle to have it slide easily, or do I want to push at some kind of a steep angle? I want to push parallel, right? Does that make sense? Okay, so we got to see if we can come up with an equation for that thing. We have to take this into account. We have to take into account the bumpiness of the materials. Well, that's something that we can't really calculate from, we just have to measure that. And actually, if you wanted to find how bumpy surfaces are, you would just look in a table, and there'd be a table of numbers called coefficients of friction that would tell you that. Coefficients of friction are going to run between values, so mu is our symbol. Call it mu. Okay, it's a Greek M, and that's our symbol for coefficient of friction. Coefficient of friction is just going to be a number. It's going to vary between. It's got to be greater than 0. 0 would be no friction, and it's going to be less than 1 unless you cheat. Unless you have something like rubber, which is flexible, and so it actually can sort of adhere to a surface and distend through pretty large displacements, and then you can actually get numbers bigger than 1, which is pretty weird. We'll talk about what that means today. That's kind of a strange concept.
You can achieve zero friction in space, right?
So zero friction would be, like for sliding friction, you could never ever actually have zero sliding friction. If two objects are next to each other and they're sliding, you can get pretty low frictions, like ice, for example. Metal on ice is pretty low friction. And if you were to spray WD-40 on the ice, you'd even get lower, but there's still some friction. At some point it would start to slow down. It couldn't go 1 trillion miles and never lose any speed, right? But yeah, in space, theoretically that would be frictionless, but it's not because space isn't empty. So even space isn't frictionless. Yeah.
So for friction coefficients greater than 1, is that like adhesive?
Well, it's kind of, but like rubber sliding on rubber is greater than 1.
Or like a glue?
Well, again, that's cheating because glue is a chemical bond.
Oh, okay.
Yeah, but even things like rubber sliding on rubber, you'll find that that's bigger than 1, and that means something kind of strange that we'll talk about here in just a second. So one part of this is if we want to calculate a frictional force, part of it is going to have to incorporate this coefficient of friction. The coefficient of friction has no units; it's unitless, right? It's just a number. So what's the other part though? So that has to do with the relative bumpiness of the materials. Totally just completely a property of the materials that are sliding past each other. It's going to be different for rubber on concrete compared to rubber on ice. Okay, so it's property of materials. The other thing we said though is how hard we're pushing them together, right? Well, what was the force that measured how hard we were being pushed on? Yeah, like by the scale. That was normal force, right? It wasn't actually weight, it was normal force. That's what normal force means, is the surface force that's pushing perpendicular to the surface. And so this ends up actually being our complete definition of friction right there. That's it. The model that we use that works really well is that frictional force equals coefficient of friction times normal force. That's it. Okay? Now, Cade asked a good question earlier. Do you have to be sliding to have friction? Well, if you do, you put a subscript K on that. K for kinetic, because kinetic means moving, right? If the surfaces are moving relative to each other, then that's kinetic friction. Okay? What if they're not? Because I can push on something, like I'm pushing on the weights right now, but they're not moving. Well, what's resisting me? Friction, right? If the surfaces were slipperier, it would move, but they're not slippery enough. It's providing some friction that's counteracting my force. So that would mean then that this would no longer be kinetic friction. This would be static friction. Okay? And then we would use a different coefficient. Okay? Turns out that if you compare the coefficients of friction, static is always going to be a little bit higher than kinetic. So for example, if we look up, I wonder if there's anything in the book. I'll just Google something here. So if we Google let's see if I can get some numbers. Okay, yeah, so for example, a tire on wet road, the static coefficient is quoted as being 0.6 and the kinetic component is being quoted as 0.4. I don't think those are probably super accurate, but it works for our sake of discussion.
What about on a tractor?
Say on a dry road, the static is quoted as being 1 and the kinetic is 0.8. Okay? So then think what that means. That means that if the tire is not sliding relative to the road, it can provide more frictional force, right?
Before it starts sliding, stop.
So before it starts sliding, so then how do anti-lock brakes work? And they really do work.
By
The-
allowing the tire to move a little bit so it's not like sliding.
Yeah.
It's just still rolling.
Yeah,
It doesn't lock up.
It doesn't lock up. Right, because once you start to skid, it's bad for a couple of reasons. It's bad strategically in terms of your capacity as a driver because you can't steer anymore, right? So that's really bad. But even beyond that, it decreases your ability to stop because once you start skidding, the tire is sliding relative to the surface, and now that's considered to be kinetic friction, right? Kinetic friction, or the kinetic coefficient, is going to be less than the static coefficient, and so you're getting less stopping force. What do anti-lock brakes typically do? Typically what they do is they just modulate the pressure in the brake fluid. Just goes on and off real quick. And so what that does then, as the tires are made of rubber, and so they can kind of deform a little bit before they start to slide. So the tire is it's gonna lock it up for a second, the rubber on the tire is gonna stretch a little bit, and then it releases it, and the tire rolls forward, right? And then it grabs it again, and so the tire gets the rubber gets kind of tweaked again, gets stretched again, and then you let it go. But the net effect of that is there's little or no skidding, right? The tire continues to roll while it's gripping the road instead of slide, and so you can dramatically decrease your stopping distance by having anti-lock brakes. It's just a really simple trick, but it's harnessing this real easy physics concept of static friction being stronger than kinetic friction, right? So what are some other types of friction? So sliding friction is typically what we talk about. This is sliding friction. What else?
Air. Rolling.
Yeah, air friction. Air friction wouldn't have to be air though, would it? It could be like water, right? We call that fluid friction. So we got another type. Fluid friction. And fluids, what is a fluid?
Oh, it's something that like.
We'll talk more about this later, but just for now, just a real basic definition.
Something that can mold any object, yeah.
Okay, it can mold any object and it can flow, right? So a fluid is just something that can flow. So water is a fluid, but so is air.
Not float, right?
Flow.
Flow. The W.
Air also can
W.
flow.
As in.
So gas, anything that can flow, like, and you can see air really does flow. Air flows over the surface of a wing on a plane, for example, right? It does flow. There are different kinds of fluids. Air is what we call a compressible fluid because it can be squeezed. Water is not. Water is incompressible, essentially. Water doesn't really change its volume no matter how much pressure you put on it, right? So, but they're all fluids. Glass is a fluid. You ever notice when you look at an old building, the windows look kind of distorted because the glass is actually, the weight of the glass has caused it to flow down towards the bottom of the window, so they're thicker at the bottom than they are at the top. So it does, it moves very slowly, but it is a fluid. Okay. So fluid, we're probably not talking about glass when we're talking about fluid friction. Usually fluid friction, we're talking about moving through some kind of a fluid and it's going to resist the motion, right? So would you agree that if you were to shoot a bullet into water, it's going to slow down a lot quicker than it would if you were shooting a bullet through air? But shooting it through air makes it slow down a lot quicker than if you were shooting it through a vacuum, right? Vacuum, there would be almost no friction, right? Essentially no friction.
What friction would there be?
There's still going to be, there's no such thing as completely empty space, nowhere in the universe. There's going to be some hydrogen, this really small amounts, but there's always going to be some. Okay? What else? I heard rolling friction.
Yeah, I said it.
I said that first.
Rolling friction, we don't have to get into too much detail, but it's actually kind of complicated. Rolling friction would be like a tire rolling on the ground, right? What's going to be lower, rolling friction or sliding friction?
Rolling.
Obviously much lower, right? Rolling friction, that's why, the wheel is a good thing. The wheel is a really pretty efficient way to travel by rolling. What causes rolling friction? Well, what do you think? What causes rolling friction?
The surface that you're rolling.
Moment.
The
Momentum.
normal forces.
Yeah, what are the interactions there that would cause, do you think, that would cause there to be any friction at all?
You said when they come together they like stick together a bit.
Yeah.
Oh, so pulling it back up.
Yeah, so when you separate, like if you're thinking about a tire on the ground, the tire's getting smushed into the ground, to use a technical term. And when you smush it into the ground, it's the little pores in the rubber are being shoved onto the little bumpies on the road. And then when you pull them apart, you have to kind of, there's gonna be some welding in there, right? So you have to, there's a little bit of stickiness there. So would you expect there to be lower rolling friction on a soft tire or a hard tire? Yeah, and that's a big thing. If you were gonna be a mechanical engineer, you might spend your entire career working on just developing like working with chemical engineers to develop rubber compounds that decrease rolling friction. That might be your life's project, where you get to be just the world's foremost expert on that. But there's a big difference. You can, like when you buy an expensive tire, one that's got a really low coefficient of rolling friction.
It also tacky.
So then that's gonna mean you get better fuel economy, but what's the downside of that?
It's not as safe, because when you have to slam on brakes, it's not good.
Yeah, when you gotta stop, then you're giving up a little bit of the stickiness, right? And so what you really want then is you wanna have kind of the best of both worlds, and that's why there's all these hundreds of different compounds of rubber that would, try to do both really well. And so, it's complicated, but do you suppose that, like, what do you think would have a lower coefficient of rolling friction? Wheel on a train or a wheel on a car? Train. Yeah. Yeah, but trains also skid pretty easily, don't they? Okay. All right, so there's friction. I was gonna show you something. How much time we got? 10 minutes. Yeah, this is pretty cool. I just found this today. This is. Okay, have a look at this. This is friction, right? So what do you know? What's one of the things we know about friction? When you, and just everybody do this. Humor me and just do this for a second. What do you notice? And when it's cold, you do that, don't you? You actually, what's going on there?
Producing heat, producing energy. The energy that your muscles are exerting are being turned into heat in your hands.
Okay, how?
Science.
Magic. Kind of. Right, so the particles in your hands, when you do this, what's going on? Well, they're getting moved, vibrated back and forth, right? They're welding and unwelding, welding and unwelding, and so they're vibrating back and forth as you move them. And as we're gonna find, that's what we're gonna come to call kinetic energy. And so that means that there's some energy that's being lost to heat there, right? So when you rub things past each other, you're losing, right? Through kinetic energy. Now watch this. This is pretty amazing. So all this is, well, you'll see. I'm not gonna explain it. Have you seen this? So they're together, separate them a little bit, get one spinning.
You could start like flying off of it.
Eventually, I think it would. It does bulge out though.
Yeah, touch it.
I want to feel that surface once it cools down.
Yeah.
That has to be so. Well, I guess it's got it now. That's how they weld things for NASA.
How about that?
Another one.
So that's how they're making those parts.
That's awesome. Let's do this one. Money Machine 2.
What's this?
Find out.
Yes, beauty. Yeah, we can't watch it. They don't.
Yeah, it's my time or something.
High def.
Like huge, like that literally goes around.
Hey, that's a strong motor.
It's really
Okay. That's got a lot of torque, is what we'll talk about later.
Close the ad. Close the ad.
physics. Well, enough Hebo advertising, but I mean, anyway, that was pretty cool.
No,
I'll put a little.
what about the last half of it?
I'm almost
Like,
done straightening.
I bet they show some really cool stuff in the last half.
Yeah, while I take roll, you guys can watch.
I'll take roll, you guys can watch. That was back.
Probably just why the scale.
No, I think they use silly putting for that.
Well, I mean,
This is just so funny.
That's impressive.
Yeah, you thought I was weird when watching videos, now you like it. That's what I thought.
All I watched is how it's made. That's just.
Yeah.
How it's made is
That's
pretty
why
good.